Now, the challenge that we face today is that classical key distribution will be vulnerable to attack by quantum computers. RSA, Diffie Hellman, and Elliptic Curve Diffie Hellman, they all rely on the computational complexity of certain mathematical problems, such as, for example, factoring large numbers into prime factors. In 1994, a mathematician named Peter Shor discovered what is now known as Shor's algorithm. Shor's algorithm enables a sufficiently powerful quantum computer to factor large numbers in seconds instead of millions of years. Now, fortunately, or perhaps unfortunately, the quantum computers that exist today are still too small and too unreliable for running Shor's algorithm. But the expectation is that at some point in the not too distant future, we will have a quantum computer that is both sufficiently large and reliable to actually run Shor's algorithm. And that day is referred to as Q-Day. From that point on, existing protocols such as RSA or Diffie Hellman or Elliptic Curve Diffie Hellman will no longer be secure. So what can we do to prepare for this Q-Day? Now, there are three approaches. The first approach is called post-quantum cryptography, or PQC. Here, we use different mathematical problems, such as, for example, lattice-based cryptography. And these new mathematical encryption algorithms are believed to be safe against attack, even by a quantum computer. The second approach is called quantum key distribution, or QKD. Here, we use the quantum mechanical properties of photons to protect the key exchange from attack by an eavesdropper. And the third approach is called quantum secure direct communications. Here, we still use the quantum mechanical properties of photons, but we don't use it to protect the key exchange, but rather the data transfer itself. Now, in this seminar, I will focus on QKD protocols. In particular, I will focus on the second generation of such protocols, which are based on entanglement and interference. These advanced protocols solve many of the problems that are associated with the first generation of QKD protocols, which are the so-called prepare and measure protocols. Entanglement and interference-based protocols are more secure against side channel attacks, and they're also more future-proof in the sense that they lay the foundation for other types of quantum networking, such as distributed quantum computing, distributed quantum sensing, and longer term, the quantum internet.